So when we have odd number electrons in molecules, we have two ways of doing it. The first way is just making sure that the more electronegative element gets a complete octet, and the less electronegative element will have 7 instead of 8 electrons. But with formal charge, we can also decide the best using formal charge. And the two processes usually will give the same answer also. But by using the formal charge process, we want to see either zeros on everything for the formal charge or the negative charge on the more electronegative element. So covalent bonds are not always equal bonds. So if we have an equal bond, like in hydrogen, or the two atoms are identical, the electrons are shared equally between the two atoms. This is a nonpolar molecule. There's no charge separation between the two atoms. But if we look at hydrogen fluoride, we're going to have the electrons spending more of their time over by the fluorine, which is more electronegative. The fluorine pulls the electrons over toward it. So the electrons are spending more time by the fluorine. The fluorine has a partial negative charge on it, and the hydrogen has a partial positive charge. This makes it into a polar covalent bond because the electrons are no longer shared equally between the nuclei. And this will affect physical properties of the condensed phase, which we'll see later on. We measure this unequal sharing of electrons as a property called electronegativity. There's a couple ways of measuring this. We're using one of those methods, the Linus-Pauling method. And this is a process of using bond energies between the pure compounds, identical molecules, and then the compound containing different molecules. So we're not going to have to worry about calculating any electronegativities from this process. The values of these electronegativities run from a high of 4.0 for fluorine, the most electronegative element, down to a low of 0.7 for francium. We do not have to memorize this table of electronegativities, but we're going to either make it available or use some reasonable assumptions in determining whether molecules are polar or nonpolar. Fluorine is the most polar element, most electronegative element here, with a value of 4.0, and then it's going to drop off both toward the left and down columns. And we're going to be using a difference of, we're going to be comparing the difference of electronegativities to decide if things are polar or nonpolar, and for the bonds, and then using symmetry of the molecule to determine if the molecule is polar or nonpolar. The cutoff is 0.4, so anything combined with fluorine is going to be greater than a 0.4 difference. So anything combined with fluorine is going to be polar. We do have a couple things that have similar polarities, electronegativities. Nitrogen and chlorine are identical at 3.0. Carbon and sulfur are identical at 2.5. The cutoff here is normally a difference of 0.4. Let's go back to the table here. 0.4 is the difference between carbon and hydrogen. So we've got 2.5, 2.1, that's 0.4. All hydrocarbons are nonpolar. So some authors put 0.4 as being polar, some authors put 0.4 difference as being nonpolar. I take 0.4 and less to be nonpolar, and then a difference of greater than 0.4 is going to be polar. we don't have to worry about hydrocarbons because we just know that anything that contains only carbon and hydrogen, a hydrocarbon, is going to be nonpolar. So if we have this separation, charge separation, a difference greater than 0.4 as in hydrogen fluoride, which is a difference of 1.9, then the electrons are spending more times on one side of the molecule. That side of the molecule, we would put a partial negative. We would identify it with a partial negative. And we're using a lowercase Greek letter delta for our partial. So partial negative is delta negative, partial negative, to show one side of the molecule being has a negative charge, partial negative side. The other side will have a partial positive side. We can also show it with an arrow pointing from the positive to the negative side, with the back side of the arrow having a cross to represent the positive side. So if we have a diatomic molecule with a polar bond, it's going to be a polar molecule. There's no way that the molecule can bounce off the charges to make it into a nonpolar molecule. But when we have bigger molecules, we can have polar bonds and occasionally a nonpolar molecule because the symmetry of the molecule will cancel out the effects of the polar bonds. Generally, this will occur when all the attached atoms are identical and there's no lone pairs on the central atom. This is for octet-obeying structures. Another way of saying this is that the electron structure and the molecular structure are identical. So when we have identical atoms attached to the central atom and the electron and molecular structures are identical, then we have a highly symmetric molecule that even if we have a polar bond, will end up with a nonpolar molecule. So an example of that would be carbon tetrachloride. The tetrachloride structure is highly symmetric. It forms a tetragon, a four-sided, equal-sided structure. So it's highly symmetric. So the mildly polar carbon-chlorine bond is canceled off in the overall molecule. So it has both a tetrahedral electron and molecular geometries. And the molecule ends up being a nonpolar molecule. It has been a common nonpolar solvent for dissolving grease. Trigonal planar electron and molecular geometry molecules like sulfur trioxide. So it's a equilateral triangle, forms an equilateral triangle, which also is highly symmetric. So all the polar bonds between sulfur and oxygen just cancel each other out, leaving us with a nonpolar molecule. Or if we have a linear molecule from linear geometry, so we got two identical attached atoms onto the central atom. This creates a tug-of-war between the polar bonds, carbon and oxygen, in opposite directions and equal strength. So then there's no win in that pull, and we end up with a nonpolar molecule. Dipole moments are reported in Debye's, which is a related to coulomb meter. Coulomb is charge, unit of charge, and meter, of course, is distance. Bond strength is the energy required to break a bond in a gas phase. We do these things in the gas phase to get rid of other effects that occur in the liquids and solids. So bond strength or bond enthalpy is the energy required to break a bond in the gas phase. And we're not going to have to memorize these bond strengths or bond enthalpies. But we can use these to estimate enthalpies of reaction. See, so in this table is all single bonds. We see a range of values from hundreds of kilojoules per mole up to 400s kilojoules per mole. For double bonds, we see a range from the lowest of 400 up to just about 800 kilojoules per mole. And then for triple bonds, we're running from 800s up to 1,000 kilojoules per mole. So we see with these bonds that they increase as you go from single to double and double to triple. We can use these bond energies to estimate enthalpies of reaction. This is not a perfect process. The bond energies vary a little bit depending on the molecules that they're in, but they do give us a reasonable estimate for enthalpies of reaction. So our enthalpy of reaction is going to be the sum of all the bonds broken, the enthalpies of breaking bonds, minus the enthalpies of all the bonds formed. So you just have to keep track of the bonds that are being broken and formed, then add up the values for the bonds broken and subtract the values for the bonds formed. So for the reaction, hydrogen plus chlorine gives us hydrogen chloride. We're going to break a hydrogen-hydrogen single bond and a chlorine-chlorine single bond, and we're going to form two hydrogen-chlorine single bonds. So we look up the value for the bond energy of hydrogen, add on the bond energy of chlorine, and subtract off two of the bond energies of hydrogen with chlorine, and we get an estimate of minus 184 kilojoules for this reaction as written. And this reaction as written is for two hydrogen chlorides. So if we want the enthalpy of formation for a single hydrogen chloride, a single mole of hydrogen chloride, then we're going to take this one for the reaction, divided by how many hydrogen chlorides we have in the reaction, and we'll see that it's negative 92 kilojoules per mole for hydrogen chloride. The actual value we could look up is 92.31. So this process gives us a reasonable, a good estimate of the actual enthalpy of this reaction. For the reaction of hydrogen with iodine to produce hydrogen iodide, same process. We're going to add up the hydrogen bond, the iodine bond, and subtract off two of the hydrogen iodide bonds. This will give us a negative 9 kilojoules for the reaction as written. Since there's two hydrogen iodides in there, we divide 9 by 2 to get a negative 4.5 kilojoules per mole for hydrogen iodide. We did this already. As we increase the bond order, the bond length decreases. So as you go from single to double and double to triple, our bonds get shorter and stronger. And our bond lengths here. So we see carbon single bond is 1.54 angstroms. Angstroms 10 to minus 10 meters. Carbon-carbon double bond is shorter, 1.34. Carbon-carbon triple bond is shorter, 1.20. Carbon-nitrogen single bond, 1.43 angstroms. Double bond, 1.38. Triple bond, 1.16. So as we increase the bond order, we are making the bond shorter. Fun.